I imagine most of you know about the party game called Mafia, but in case you don't know, here's a quick explanation. A number of players would sit together in a room, and some would be randomly selected to be Mafia. The remainder will be the villagers. The Mafia would know each other's identities, but the villagers don't know who are Mafia. In every round, there's two phases, the day phase and the night phase. In the day phase, the survivors of the game would select one person to eliminate, usually through a process like voting. In the night phase, the Mafia would select one villager to kill, and this villager would be eliminated from the game. They cannot participate in the discussion in the following day phase. The game ends when either the Mafia is eliminated, in which case the villagers win, or if at least half of the remaining players are mafiosi, in which case the Mafia win. But how many players should be Mafia, and how many should be the remaining villagers? In common setups of this game, we often see 2 Mafia vs 5 villagers, 3 Mafia vs 6 villagers, 3 Mafia vs 8 villagers, 4 Mafia vs 9 villagers, and so on. So you might say maybe the number of Mafia is around half the number of villagers. In other words, the Mafia make up 1/3 of the players. In practice, these setups really do result in relatively even games. The Mafia win around the same number of times as the villagers. But the trend does not work like that. If we had a game with 1 million players, then we only need around 1,000 Mafia for a relatively even game, although this would be a logistic nightmare to actually play. The number of Mafia only needs to be around the square root of the number of players. I'll give a quick informal argument for why this is the case. Here I've drawn a number of pie charts representing the proportion of players that are Mafia in each round. In the beginning, 2 out of 7 players are Mafia. On the first night, one of the villagers are killed by the Mafia. On the next day, one of the Mafia are successfully eliminated through the voting process. On the next night, another villager is killed, and now 1 out of 4 players are Mafia. As we continue, the fraction of Mafia increases, and eventually, out of the 2 players, one of them are Mafia, in which case the Mafia win. Of course, there's strategy in an actual game of Mafia. Most of these strategies revolve around psychological aspects of lying around other players. But let's suppose for a moment that the players, especially the Mafia, are skilled at the game. So there's literally no information that can be used to distinguish Mafia from villagers. In this case, the players have no choice but to randomly select one person to eliminate in the day phase. In the night phase, one of the villagers is guaranteed to be eliminated, since the Mafia know where the other Mafia are. If the day phase eliminations are random, then the whole game is stochastic. But let's simplify it further into a deterministic process. Instead of keeping track of the state of individual players, we only track the total number of players and the approximate fraction of players that are Mafia. In particular, we don't track the actual number of Mafia, and if we multiply our approximate Mafia fraction by the total number of players, we might not even get a whole number. But whatever, this is just a simplified model. In this simplified model, after the day phase, the total number of players drops by 1, but the Mafia fraction is unchanged. This represents the fact that we eliminate players randomly, since the probability that we happen to eliminate one of the Mafia is just the Mafia fraction. The night phase updates our model state in a more interesting way, even though it's the less interesting phase of the actual game. So we know that the approximate number of Mafia players is just the Mafia fraction times the number of players. On this video, I use F to denote the Mafia fraction and N to denote the number of players. So this is just F times N. After the night phase, we have n-1 players, of which the number of Mafia is still around F times N. So the new Mafia fraction is F times N over n-1. We can update the model state over each round until the number of players drops to 1. Assume the number of players n is odd. It doesn't really matter though. We start with Mafia fraction F, and we multiply it by n over n-1, then n-2 over n-3, then n-4 over n-5, until we finally multiply by 1 over 2. That product is pretty hard to evaluate, and really we have no need to find the exact value. A general idea is good enough. To help deal with this product, let's turn it into a sum by taking the natural logarithm of the whole thing.
So now we have ln of f plus ln of n minus ln of n minus 1 plus ln of n minus 2 minus ln of n minus 3, and so on.
So we have pairs of ln terms being added together. Each pair is the difference between the natural log of two consecutive integers. We can use Taylor's theorem to find upper and lower bounds for each pair. By using this theorem, we find that the difference between ln of n and ln of n minus 1 is approximately 1 over n minus 1, plus or minus something on the order of 1 over n squared. We can get tighter bounds by appealing to properties like convexity, but this is good enough. Using the approximation, the natural log of the Mafia fraction in the simplified model at the end of the game is around ln of f plus 1 over n minus 1 plus 1 over n minus 3, and so on, ending at plus 1 over 2. The error is bounded by the sum on the right, 1 over 2 squared plus 1 over 4 squared, and so on until 1 over n minus 1 squared, all times 1 half. We can bound the sum from 1 over n minus 1 to 1 over 2 by comparing the series against the integral of 1 over 2x. By summing the areas of rectangles to represent the series sum, in other words, by representing it as a Riemann sum of the integral, we can overestimate the area by aligning the right edges of the rectangles against 1 over 2x, and using the integral for all terms after 1 over 2. This gives 1 over 2 plus the integral of 1 over 2x from 1 to n minus 1 over 2 dx. We can underestimate the area by aligning the left edges of the rectangles. This gives the integral of 1 over 2x from 1 to n plus 1 over 2 dx. Now we just simplify things to get upper and lower bounds. One last thing to point out. Remember the error term that adds 1 over 2 squared up to 1 over n minus 1 squared? Even if that sum goes on infinitely, we can bound it by a finite value. Actually, it can be proven to be at most pi squared out of 48 through some clever mathematical sorcery. But even if we didn't know this, we could just bound it with another integral method, and we can easily show that it's finite. So here are the upper and lower bounds. Both are on the order of ln of f plus 1 half ln of n. If we want the Mafia fraction in our model to be more than 1 half at the end of the game, which is strong evidence that the Mafia will win, then we only need ln of f to be around negative 1 half ln of n, plus some constant terms like ln of 1 half, pi squared out of 48, and so on. That means the Mafia fraction at the start of the game only needs to be some constant times 1 over square root n, since the natural log of that is a constant minus 1 half ln of n. So we've established that if we use the simplified model with no probabilistic woes, then the Mafia fraction only needs to be around 1 over the square root of the number of players, for the game to end with a Mafia making up the majority of the players. In other words, a Mafia victory. It can be argued that the real game is not really that far off from our model. Originally, the day and night phases are supposed to alternate. If we had a large number of rounds, we can imagine creating superphases which clump the day and night phases together. If we clump enough day phases together, then the randomness of the daily eliminations averages out due to the law of large numbers, and the behavior of this superphase-based game is similar to our simplified model, where one superphase of the game is like one phase of the simplified model. Pushing all the night phases to the start favors the villagers, and pushing the night phases to the end favors the Mafia, but both only need the number of Mafia to be around 1 over the square root of the number of players in order for the Mafia to have a reasonable chance of winning. And so should the actual game where the phases are alternated.